Okay, so the purpose of this video is to further explain the traits of rational functions that we started learning about in the previous video that we started learning about on Tuesday. So in this class, we talked about last time how to find discontinuities and how to classify those as wholes or vertical asymptotes. So in this video, we're going to talk more about how to find other traits on the graph. Now, some of the important traits that you need to know about rational functions are x-intercepts, y-intercepts, and something called end behavior. So x-intercepts we've typically found in the past by letting y equal 0 and solving for x, and y-intercepts we typically found in the past by letting x equal 0 and solve for y. So we're going to do the same process here. It's just there's a couple of things to think about here. So if I were trying to find a y-intercept of this first function that I have, I would let x equal to 0. So each of these x's would have a 0 plugged in for it. And on top, that would give me negative 3 times 2, which is negative 6, over 1 times negative 4, which is negative 4. Negative 6 over negative 4 is positive 3 halves. So I would expect there to be a y-intercept at 3 halves. And if I turn the graph on, there it is, right there. So if I went to the second example, I would do the same thing. Just notice if I plugged in 0 into all these x's, the first factors here, because there's one of them on top and one of them on bottom, would give me a common factor on top and bottom, so that fraction would automatically simplify. So really, this first part here would give me 1, because it's negative 5 over negative 5. So really what I need to pay attention to are these, 2 over negative 1. So I have a y-intercept of 2. And indeed, there it is. Now, I could do the rest of these in the same way. Just notice on this third one, when you plug in 0, you get 0 on top, and on the bottom you would get negative 2. 0 divided by negative 2 is 0, so there would be an x-intercept at the origin. Y-intercept, sorry, at the origin. All right, so that's with y-intercepts. So with x-intercepts, what we typically have done is set y equal to 0 and solve for x. So if I did that with this first one, I would let this y be 0, and I'd have this fraction here equaling to 0. Now that's a rational equation, and we've solved these before. Normally we find the common denominator first, but there'd be only one fraction that would equal to 0, and then we multiply both sides by that common denominator to get rid of it. So I would have x minus 3 times x plus 2 equals this 0 over here times these factors. So essentially that would leave me with x minus 3 times x plus 2 equals 0. So my x-intercept should be 3 and negative 2. So if I click through on that, you see we have an x-intercept at negative 2 and an x-intercept at 3. Now, y-intercepts are very straightforward. X-intercepts require a little more thought, but it's connected to solving rational equations like we talked about before. So if I went to the second one, I will follow the same process. I let y equal to 0, so this would be a 0. And then I multiply both sides by the common denominator. That would give me x minus 5 times x plus 2 equals 0. Now, that means that x would equal 5 and x equal negative 2. But remember, one of the things that we're supposed to do when we're solving a rational equation is to actually make sure that the solutions aren't excluded values. And if you check 5, it is an excluded value. So really, those two solutions I got, 5 and negative 2, only one of them is truly an x-intercept, and that would be the negative 2. So when I click through on this, you see there's only one x-intercept. It occurs at negative 2. And what happens at 5? Well, there's a factor on top and a factor on bottom that give you that thing, and it cancels away. So there should be a hole at 5. And there is. Note that keeps you from having the x-intercept there. All right. So if I were finding the y-intercept on this third one, I'd do the same thing. I would get 0. And on this last one, if I went to set this thing equal to 0, multiply both sides by the common denominator, I get x minus 3 equals 0, so I get x equals 3. But 3 is an excluded value. So the only value that I got that would work as an x-intercept actually doesn't work at all because it's an excluded value. That means this graph actually doesn't have any x-intercepts. So if I were to click through on it, you see how this gets closer and closer to the x-axis. It looks like it may eventually touch, but it doesn't actually. And I could zoom in on this forever and show you that's the case. But this levels off and gets closer and closer to 0 on both sides, but never touches it. Cool. Now, we also talked about end behavior in this class, but in order to talk about that more intelligently, I'm going to use a different medium. So, All right, so in addition to talking about x and y intercepts of rational graphs, we talked about in behavior in class. And what in behavior is the value y goes toward at the extreme left and extreme right of a graph. That says or, that should say of. Let me fix that because it's going to bother me. Okay. Now, just looking at a graph pictorially, if I had a graph that did something like this, and in behavior deals basically with what's happening at the far right and the far left of the graph. Now, that means really in behavior, all it cares about is what the arrows are doing at the ends. It has no concern with what's going on in the middle of the graph, just the endpoints. So the arrows. So if I look at the arrows, there are two ways, for example, if I looked at this arrow, there are two ways of describing what this arrow is doing. It's pointing to the left. It makes sense. It's on the extreme left of the graph. It's also pointing up. And an in behavior statement, a description of the in behavior, would actually include both of those descriptions. So if I were trying to describe this in behavior, which is called a left hand in behavior, I basically would want to talk about what x is going toward. Now, in this case, because I'm walking to the left, x gets more and more negative. If I were looking at points on the graph and I just kept walking along the graph, the x values would get more and more negative. And eventually they get so enormously negative that I could say they're getting close to negative infinity. Now, this is read out loud as x approaches negative infinity. That means you're getting really close to negative infinity without actually reaching it. Every single left-handed behavior has this because this indicates that you're going to the left on the graph, the extreme left. The thing that you have to determine when you're looking at in behavior is what the y value is doing as you go in that direction. So if you look, the arrow is pointing both left, which you've already covered, and up. So that means basically, if I kept going, the y values would get bigger and bigger and bigger. So they would approach infinity. That's called a left hand in behavior statement. Now, if I wanted to make a right hand in behavior statement, and an in behavior of a graph generally consists of both of these, right and left hand in behavior statements, this time I would be walking to the right. And as I walk to the right, the x is getting bigger and bigger, so this time it's getting close to infinity. Now, every right-handed behavior statement has this, because that's what indicates you're going to the right. And again, you have to determine what the y values are going to be doing. So the y values here are dropping down. So you would say that the y values are getting more and more negative, so they're approaching negative infinity, like that. So even if I gave you something crazy like that, again, the in behavior only cares about this and this. So this would be, take a pause and see if you can guess it. All right, so let's see if you got it right. This would say, as x goes to negative infinity, y goes to negative infinity, that this is the thing that makes it go to the left, and this is saying it's going down. And this side would be, as x goes to infinity, y goes to negative infinity. This would mean that it's moving to the right, and this would mean that it's going down. Okay, so that's a basic description of what in behavior looks like graphically. So now, if I wanted to talk about in behavior of rational graphs, I really need to talk about in behavior of polynomials first. So if I go to the polynomial, if I were to write an equation of something like x cubed plus 5x squared plus 6x minus 2, and I were interested in finding the in behaviors of this function, I want you to keep in mind that in behaviors involve really giant numbers, right? So if I had plugged in something like a billion in for x, this first term would be a billion times a billion times a billion. This second term would be a billion times only 5. So this first term would be so much bigger than the second term. And this is only a billion times 6, so it's really tiny compared to that term. And then negative 2 is almost minuscule, right? So if I made it a really, really, really big number, this term here, the one that has the highest power on it, is going to dominate more and more and more. In fact, there's a statement that says the in behavior of a polynomial is determined by its highest degree term. And again, that's because as the x's get really, really giant, that power is going to make that term so much bigger than everything else. So essentially, anytime we have a polynomial and we want to describe the end behavior, we look to the highest degree term. So if I had something like this, I basically, if I'm asking for end behavior, would ignore all of this and pay attention to this. Now, this is called an end behavior model. An end behavior model is a simple function that shares its end behaviors with a more complicated function. So the end behavior model for this polynomial would be negative 2x to the fourth. Now, if I were trying to figure out what's going on with this end behavior model, as x goes to infinity with this, I'd be plugging in a really big number for x that's positive, raising it to the fourth, which makes it even more positive, and then multiplying by negative 2. So I get a really, really big negative number. So y is going to go to negative infinity. As x goes to negative infinity, and I looked at this, I'd be taking a really, really negative number, raising it to the fourth, which would make it positive, and then multiplying by negative 2. So again, y will go to a negative infinity. Now you can actually reason through that with numbers like that, but you can also think in terms of this chart. And if you need more explanation for this, you can come talk to me about it, because we described why this was the case in class. But in behavior, with these in behavior models, depends largely on two things. You're always going to get basically kind of like a one-term power function for polynomials. And the in behavior depends on two things. Whether the degree is odd or even, so is the highest power an even number or an odd number, and then is the leading coefficient positive or negative. Now, if the degree is odd and the leading coefficient is positive, it's going to act basically like y equals x at the ends. It's going to point up and to the right. Sorry, to the right is going to be pointing up, and to the left is going to be pointing down. So as x went to infinity, that would go to positive infinity. As y went to negative infinity, that would go to negative infinity. If it's even, it's going to act like x squared. So basically, the end behaviors will point in the same direction. And x squared points upward, right? Now, if I multiplied y equals x times a negative number, that would flip the graph, and it would change the end behaviors. They would still point in the opposite direction, but in opposite directions from what we had before. And then with evens, it would flip that x squared, and it would look like that. So if I had something like I got an end behavior model of, say, negative 5x to the fifth, that degree is odd, and that leading coefficient is negative. So it would fit this end behavior. So as x goes to negative infinity, y goes to infinity. And as x goes to infinity, y goes to negative infinity. Okay, so that's how you find end behaviors of polynomials. Now that's really important because when we're dealing with rational functions, the thing on top and the thing on bottom of a rational function are both polynomials. So if I'm looking for the end behavior of one of these things, the end behavior model for a rational function will be built by taking the highest degree term on the top and putting it over the highest degree term on the bottom. Then you simplify that. In this case, that would simplify down into 1. And then you ask yourself a question. As x gets huge, what does this thing do? Well, there's no x in it. It's basically just 1. So as x gets big, it's not going to affect that value. It's going to get closer to 1. So the end behavior of this graph would be 1. Now, whenever an end behavior equals a number, we say there's a horizontal asymptote. At that number. So since it's horizontal, it would be y equals 1. So let's do another example here. If I gave you a function that looked like this, I'm going to do 3 examples here. All right, so if we're finding our end behavior, we want to build an end behavior model, and that would be the highest degree term on top over the highest degree term on bottom. Simplify the fraction. Ask yourself what happens as x gets huge. Well, that's a number, so it stays at 3/2. And you got a number, so there's a horizontal asymptote at y equals 3/2. Now, it doesn't always simplify down to being just a plain number when you simplify the end behavior model. Sometimes you can get something that looks like this. If I'm trying to find my end behavior, I build my end behavior model. And that would give me x over x squared. That simplifies down into this. Now, that still has an x in it. So when we ask ourselves, what happens as x gets huge? We would find that you get 1 over a giant number. And when you divide 1 by a giant number, it gets closer and closer and closer to 0. Now, does it ever actually reach 0? No, but it gets closer and closer to it. So my end behavior gave me a number again. It's getting closer to 0. So my horizontal asymptote is at y equals 0. Let's do one more. So I want the end behavior of this. So if I'm building the end behavior of that, I build an end behavior model, highest degree term over highest degree term, and that would simplify down into x. Now, when you ask the question here, what happens as x gets huge? As x gets really, really big, this gets really close to infinity. So that's as x gets really big, y gets close to infinity. And as x gets close to negative infinity, we get close to negative infinity. Now notice there's no end behavior that equals a number here. So basically, we have end behavior, but there's no horizontal asymptotes. So often I'll ask you to find the end behavior and then say, tell me if there are any horizontal asymptotes and if there are where they are. In this case, you would have found the end behavior and you could just say there's no horizontal asymptotes.